Now we're going to take a look at part 2 of section 11 and describe the bivariate latent transition analysis. In the picture here we show a model where you have two processes, y at the top, z at the bottom, and we have auto regressions of order 1 for each of the two variables, lag 1 modeling, and we have cross-lag modeling across time between the two processes. There has been related bivariate LTA writings. For instance, the ALTA model, Associate Latent Transition Analysis by Brian Flaherty in 2008, and has been studied and applied by Vitkevich and Villarroel, and also by Bray and others. And those three references are given in the reference list at the end. Another variation is a mover-stayer version of the bivariate LTA, and there you can have several different variations of how you specify the mover-stayer latent class variable. You could do one latent class variable for each outcome, one for both, or for only one outcome. So three different versions of adding that additional latent class variable. And you can also do a bivariate RI LTA. On slide 112, I discuss some computational considerations because they become important in this case. Bivariate LTA is time and memory demanding, I say, when you have many time points, even with only two classes, because we get so many combinations of the latent classes. Now I'm going to focus on two classes here because of the binary outcome of suicidal ideation and substance abuse. Now regular LTA with T, that is regular bivariate LTA with 7 time points, results in to the power of 14, 16,384 combination classes, which is slow but doable on a good computer. So that's pretty much the max that I want to consider on my computer. And my computer is a Dell desktop with the Intel i9 processor. It's i9-11900K, and I have 32 gigabyte RAM. Mover-stayer LTA adds a latent class variable for each outcome in its most general form, which for t equals 7 results in 2 times 2, those are the two mover-stayer latent class variables, and then 2 to the power of 14, the total number of observed variables, which will lead to over 65,000 latent class combinations. And that's out of the question for doing a practical analysis. So if you say that your computer gives you the max of 16,000 something, which is the case for my computer, then you can solve for how many time points you can handle. And I solve for x here, and x is 12. That is, since we have two processes going forward, I can handle a maximum of 6 time points. Now the t equals 8 analysis of suicidal ideation and substance abuse, as we saw, that shows more stable development after the first 3 occasions. So that suggested an analysis of the last 5 time points, so a t equals 5 analysis, which would end up, even with 2 mover-stayer variables, being quite manageable at a little over 4,000, which is a quarter of my maximum. So there you can go through a series of analysis without spending too much time. On slide 113 then, I do the analysis, the LTA for each of the two processes, suicidal ideation at the top and substance abuse at the bottom. This is for t equals 5 then. And I'm going to impose stationarity, that is time invariance of the transitions over time. The transition probabilities are the same across time. Now, the LTA model then is well fitting for in the usual 2-class model once again here it is for the last t equals 5 as opposed to the t equals 8 that we talked about before. But you get a better fit if you move to the mover-stayer model. You get a better, somewhat better log likelihood. BIC is not better because you add parameters, more parameters than you benefit from. But it's a good fit, and you get a reasonable estimate of 36% stayers. RI LTA fits the same, has better BIC because it has one parameter less, fits well in terms of standardized residuals, but you have uninterpretable measurement probabilities. So we would discard that model based on interpretation grounds. For substance abuse, you have a similar situation where you have a good fit for LTA, regular LTA, and also for mover-stayer LTA. Turning then to the bivariate LTA, where t equals 5 with time invariant transitions, we have some results here in the table. And I posted some of these runs on the website of the talk. And we note then, remind ourselves that the most frequent pattern, which is all zeros, is observed for 193 individuals. So the regular LTA, that is without mover-stayer, regular now means bivariate, has what I would call a marginal fit. In terms of the bivariate cells, it's okay, but we do have significant misfitting residual for the most frequent response pattern, 193. You could do an LTA with the mover-stayer latent class variable for both processes, and you get a little bit better fit. The BIC, however, is worse because the fit is not improving enough relative to the increased number of parameters. And you still have a misfit for 193. So once again, I would call that a marginal fit. And in this case, we don't find a perfectly fitting model. You may have to make some other adjustments. Maybe the time invariance of the transitions doesn't hold, but it is at least a marginal fit, and we're going to stay with this model LTA2C. On slide 115 then, we take a look at the LTA results in logit and odds ratio terms. So we have then these cross-lagged effects, CY on CZ, and that's CZ at the previous time point, of course. The logit estimate is 2.172 with a certain standard error, and the odds ratio is then the exponent of that, 8.77. And then you can translate that to the logit confidence interval using that standard error plus minus at 1.96 to an odds ratio confidence interval by exponentiating the confidence limits. And then you get this interval 2.45 to 31. So it does not include 1, and therefore we would say that this is a significant effect. So that would mean that the latent class variable for substance abuse at one time point influences the latent class variable for suicidal ideation at the next time point. So here we have a clear, significant positive effect. If you look at the reverse effect, the estimate is lower and the odds ratio is only 1.6. And again, translating the logit CIs to odds ratio CIs, you see that 1 is included, so that is not a significant effect. So we conclude that substance abuse influences suicidal ideation, not the other way around. That's interesting then to think that this model is actually analogous to bivariate AR1, that is a CLPM model. We don't use a random intercept. So it's a CLPM model where we have imposed time invariant cross-lagged effects. but with the added twist that we include a measurement error. Now if you try to fix the measurement error at 0 for this LTA, and you can do that, so the off-diagonal probabilities, the measurement probabilities we looked at earlier in part 1, if you fix them to 0, you find that the model fits significantly worse. If you then turn to the mover-stayer model, the second model in the bivariate analysis table that we looked at, that also points to significant CY on ZZ and insignificant ZZ on CY. And this is among the movers then, of course. Now you can go further and take a look at more detailed aspects of this analysis on slides 116. So first, let me say that in this case, we talk about class membership having values 1 and 2. So not 0, 1, but 1 and 2. So 1 is the low class and 2 is the high class. So 1 low class, 2 high class. So we can look at 4 different probabilities here. If you talk about probability now for Y being in the low class as a function of Y's previous latent class membership 1 or 2 and Z's previous latent class membership 1 or 2. We can calculate these different probabilities from the estimated model using model constraint. And I think I included an output which shows how I did that. So if you look at this carefully then, if you compare 1 and 2 and look at it a long time, you see that the difference between those two lines is that on line 2, the previous Z value is 2, that is, it's the high class. So we're comparing being in the low class for Y, given that the previous Y is in the low class, but comparing being in the low or high class for Z. So we see that the first value is higher than the second. So I'm writing this out in words here so it's easier to comprehend. Comparing 1 and 2, the effect of CZ on CY for the low CY class, by which I mean the class at t minus 1, that is 1 here. The probability of staying in this low CY class is decreased from 0.980 to 0.851 by previously being in the high compared to the low CZ class. So if you're in the high class for Z, you have a lower probability of staying in the low class for Y. So in that sense, Z has an effect on Y. You may want to think about that at your own pace. I find it a complex statement, but interesting statement. And then you can compare 3 and 4, where you look at Y being in class 2, the high class at the previous time point, and what the probability is to move to the low class for Y, 4 different starting points for the Z class, 1 or 2. So the effect of Z on Y for the high Y class, that is class YT minus 1 equals 2, those two values here. The probability of transitioning from the high to the low CY class is decreased from 0.09 to 0.011 by previously being in the high compared to the low class. So if you're in the low class here, if you're in the high class here, you have a lower probability of moving from the high Y class to the low Y class. So that makes sense. Now you can test these probability differences using model test. And you get a testing that both of them are the same, that the difference between 1 and 2 and 3 and 4 are 1 and 2 is not existent, and the difference is not existing between 3 and 4 either. Gives a chi-square with a sort of ambiguous outcome. But if you test the first difference, 1 degree of freedom, then you see more of a sign of significance. That is, there is some difference in those probabilities, but less so in the second difference, 3 to 4. So one could say that this 1 to 2 effect is the most important one, and presumably the one that gives the significant effect of Z on Y, Z influencing Y. Okay, and then final comment then on bivariate LTA. LTA is of course also possible for ordinal variables, polynomous ordinal variables, and nominal variables, and many indicators. And I did an analysis of this 5-category alcohol risk outcome that we looked at for data set 1, the combined alcohol study, for 5 time points. I took every other time point over those 8 weeks. I did that with up to 5 classes with the regular LTA and up to 4 classes with mover stayer, LTA, and RLTA. So that's quite possible. You don't have to have as many classes as there are observed categories of the latent class indicator. So then remaining questions here then, in terms of doing general LTA bivariate analysis. How would you bring in ordinal variables of the 2-part modeling kind, which I will describe in the next section, into the LTA? That's an open question. And how do you do a bivariate LTA for, say, alcohol risk combined with a continuous stress variable to capture cross-lagged effects? Can you do it without having to introduce a latent class variable for the continuous stress variable? If so, how would you do it? So there are open methods research questions.